Good morning, students. Welcome to our video lecture. In the last lecture, students, we had discussed all the truth tables and basics of logical connectives. Students, basically, we have two types of logical connectives. One is AND, other is OR. The truth table and all we have already discussed. Then, students, we had prepared the truth tables. We have prepared the truth table of AND, that is device P, Q, P, and Q, T, T, F, F, T, F, T, F. It is only true when both the component statements are true. Otherwise, students, AND is false. Then, students, OR P, Q, P or Q, T, T, F, F, T, F, T, F. OR is true when one or both the component statements are true. OR is false. So it is only one case when both the component statements are false. So this is what, students, we had discussed in the previous lecture. Truth tables are not given, students, in our textbook. So I am suggested you students you should learn, write and memorize the truth tables. Okay, students, now we are starting exercise 14.3. Sum number 1. For each of the following compound statements, first identify the connecting words and then break them into component statements. Let us revise, students, the definition of simple statement and compound statement. Students, let us revise the definition of simple statement and compound statement. What is simple statement, students? A statement which cannot be further broken down into two or more statements is called a simple statement. What is a compound statement, students? A statement which can be broken down into two or more simple statements is called a compound statement. So let us, students, do question number 1 of exercise 30. All rational numbers are real and all real numbers are not complex. So the connecting word is AND. Exercise, students, 14.3, question 1, part 1. Connecting word in, students, and let us write the component statements. First is P and students, second is Q. Now the statement P will be like this: all rational numbers are real. All rational numbers are real. And students, the statement Q will be all real numbers are not complex. All real numbers are not complex. So simply, students, we are to identify the connecting word, and after identifying, students, the connecting word, students, we have to simply, you can say, write the component statements. Now, students, second, all square of an integer is positive or negative. So first of all, I write connecting word is or Then component statements. Component statements. P square of square of an integer is positive. Okay. Square of an integer is positive Q. Square of an integer is negative. So this type of some students are comparatively very easy students. We have to simply tell what is the logical connective, and then students we have to write the component statements. Okay. Third, the sand heats up quickly in the sun and does not cool down fast at night. So connecting word is and. Connecting word is and. Then component statements are: first, P. The sand heats up quickly in the sun. The sand heats up quickly in the sun. Q. The sand does not cool down fast at night. The sand doesn't cool down fast at night. So students, these are comparatively very easy sums. And students, we have to only simply write the component statements and connecting word. So very easily students you can do the sum. Fourth statement I am doing pull. The statement is x is equal to 2 and x is equal to 3 are the roots of quadratic equation 3x squared minus x minus 10 is equal to 0. So the connecting word is and. Statement P, x is equal to 2 is the root of quadratic equation 3x squared minus x minus 10 is equal to 0. Statement Q, x is equal to 3 is the root of quadratic equation 3x squared minus x minus 10 is equal to 0. So students, this type of questions are very simple. Simply write the connecting word and then break the compound statement into component statements. Okay students, now today we are going to complete exercise 14.3 and we are going to do two new topics which are, you can say, the basics of two sums in exercise 14.3. Now, students, all of you please pay attention. Question number 4. The logical connective or, students, or is used in two broader sense. One is inclusive and students, the other is exclusive. One is inclusive or other is exclusive. Now in exclusive and in inclusive students, what particular application do we have? In inclusive or exclusive students, what particular application we have? When only one of the two options is possible, only one of the two options, then students it is exclusive. And when both the options are possible, then students it is inclusive. Now let me give you an example of both. First of all of you remember, logical connective OR is basically used in two senses. One is exclusive sense and other is inclusive sense. Say you go to a restaurant and after your dinner you can be either served a cold drink or students you can be served an ice cream. Both the options are not possible, only one of the two options, so I can say OR is used in exclusive sense. You have two options, either you can be served a cold drink or students you can be served an ice cream, but you cannot be served both even though you want. Then students, as a KYC norm, know your client norm, you can either have an Aadhaar card or you can have a ration card. So even if you have both, your KYC is done. Even if you have only one, your KYC is done. So here OR is used in which sense? Inclusive sense. So when of the given option only one, then OR is used in exclusive sense. And when of the given options both are also possible, then OR is used in inclusive sense. So when of the given option only one, then exclusive, and both, then students inclusive. Let us apply this students in question number 4. State whether OR is used in the following statements in exclusive or inclusive sense. Give reason for your answer. Sun rises or moon sets. Sun rises or moon sets. We are doing exercise 14-20 students question 4 part 1. So here OR is used in exclusive sense because only one of the things takes place. When sun rises, at that time moon doesn't sets. So OR is used in which sense? Exclusive. To apply for a driving license, you should have a ration card or a passport. When you apply students for a driving license, either you should have a ration card or you should have a passport. But even if you have both, license will be issued. So both options possible. So students, we write OR is used in inclusive sense. And last but not the least, the third statement, all integers are positive or negative. Now at a time, one integer is either positive or negative, only one option. So OR is used in exclusive sense. So out of two options, students, when only one option is possible, exclusive sense. When both the options are possible, students, we can say inclusive sense. So students, OR is basically used in two sense. One is inclusive, students, and the other is exclusive. One is inclusive, students, and the other is exclusive. So this, students, we have to perfectly remember and memorize. So don't worry, students, this is a very important theoretical topic. The logical connective OR is basically used in two sense. One is inclusive sense and other is exclusive sense. Now students, today's master topic which we are going to do, and that is mathematical quantifiers. Students, today's master topic which we are going to do, and that topic is mathematical quantifiers. Mathematical quantifiers. This is a very important topic. Now, page. In mathematics, students, we have basically two quantifiers. First is universal and second is existential. In mathematics, students, we have basically two types of quantifier. First is students universal and second is students existential. Universal quantifiers are understood by the words or phrases for every, for all. Symbol of universal quantifiers is existential quantifier is understood by the words there exist, and the symbols. The symbols are not given in the textbooks, so students you can easily understand. So in mathematics, students, we have two types of quantifier. First is universal quantifier, second is existential quantifier. Universal quantifier is understood by the words for every, comma, for all. Existential quantifier is understood by the words there exist. Symbol of universal quantifier is inverted A, but I don't call this as an inverted A, just for your knowledge. And the reverse E is the symbol for existential quantifier. Now students, the formula which we remember, negation of a statement with universal quantifier is existential quantifier and negation of P. Negation of statement with existential quantifier and P is universal quantifier and negation of statement. This is not given in our textbook. So please students memorize and write down this formula, which is very important. Each of the quantifiers are correspondingly students negation of each other. Each of the quantifiers students are correspondingly the negations of each other. Then students, we have De Morgan's law, as we have in set theory, same we have in logic. Negation of P and Q is negation of P or negation of Q. Negation of P or Q is negation of P and negation Q. Negation of N is OR. Negation of OR is N. These are called De Morgan's laws for logic. These are students De Morgan's law for logic. Very important. You can note down this in a paper and you can say, you can staple that along with the textbook. So formula based, truth table based is not given students in our textbook, and this is again you can say a very crucial part. This is again students a very integral part of the entire chapter. Okay students, now we are doing main question 2 and main question 3. Identify the quantifier in the following statements and write the negation of the statements. So once again summarizing the mathematical quantifier, students please pay attention. We have done something more than given in the text. There are two types of quantifiers, universal and existential. Universal quantifiers are identified by the words for every, for all, and the inverted A is the symbol. Other quantifier is existential quantifier, which is understood by the words there exist. The symbol is inverted. Negation of universal is existential, negation of existential is universal. So I can definitely say the two quantifiers are respectively or correspondingly the negations of each other. Then students, I have given you the De Morgan's laws. Negation of P and Q is negation P or negation Q. Negation of P or Q is students negation P and negation Q. So remember this, write this as formulas. It will be very useful for sums. So I am now doing main question 2 of exercise 14.3. Sorry students, 14.3. There exists a number which is equal to its square. So what is the quantifier? There exists. Exercise 14.3, question 2, part 1. The quantifier is there exist. And I can even say this as existential. Our textbook does not specifically name the quantifiers, but even I can write the quantifiers existential or there exist. Now what is the statement? There exists a number which is equal to its square. So negation of existential quantifier is universal quantifier, and then we have to simply add the statement, negation of the statement P. So the statement is there exists a number such that square of the number is equal to the number. So there exists, we have negation as for every. So I can write for every number, the square of the number is not equal to the number. So the negation is for all numbers, square of the number is not equal to the number. Back answer is written in different way. There exists a number which is equal to the square. So there does not exist any number whose square is equal to the number. Or I can write for all numbers, square of the number is not equal to the number, the meaning is same. So definitely students, so here the answer is written in a different way. So there does not exist any number whose square is equal to the number, or else I can write for all numbers, square of the number is not equal to the number. So always remember the negation for there exists is for all. Now second statement, for every real number x is less than x plus 1 for every, so quantifier is universal, but here we can write there exists universal or for all. For every, I can definitely call this as universal. So what is the negation, students, of the statement? The statement tells us that for every real number x, x is less than x plus 1. Means there exists a real number x such that x is not less than x plus 1. There exists a real number x such that x is not less than x plus 1. There exists a real number x such that x is not less than x plus 1. So negation for every is existential, and negation for existential is for average students. That we have to remember. Okay, some quantify and then students you will write negation. There exists a capital for every state in India. I think students the statement is wrong. For every state there is a capital in India. I think this statement is slightly even wrong in the textbook. Every state in India has a capital. This is the statement. You can change the statement. So the quantifier is for every. For every means universal. Every state in India has a capital. This should be the statement, not as given in textbook. Every state in India has a capital. So, what should be the negation? There exists a state in India which does not have a capital. There exists a state in India which does not have a capital. This should be the correct answer. So students, mathematical quantifiers are very frequently used, especially in analytical geometry, coordinate geometry and other aspects. Mathematical quantifiers are frequently used in analytical geometry and analytical mathematics. Now students, we are doing sum number 3 of exercise 14.3. Check whether the following pairs of statements are negation of each other or not. Give reason for your answer. First statement is x plus y is equal to y plus x is true for every real numbers x and y. X plus y is equal to y plus x is true for every real numbers x and y. Quantifier is for every. For every means universal. So there exist real numbers x and y such that x plus y not equal to y plus x should be the negation. But what is given? There exist real numbers x and y for each x plus y equal to y plus x. In the negation we have x plus y not equal to y plus x. So the given pairs of statements are not negations for each other. In third sum, students, we can definitely say that the given pairs of statement are not negations of each other because the negation of the first statement will be there exists real numbers x and y such that x plus y are not equal to y plus x. But in the second statement, students, we are given equal to. So main question 3 of exercise 14.3 students we have done orally. Remember, the given pairs of statements are not negations of each other. So students, here we conclude our exercise 14.3. We have completed 14.3. To today two new things we have studied. First is use of or in two sense. One is exclusive, other is inclusive. Only one option, then exclusive. Both options are possible, then inclusive. The second important topic is mathematical quantifiers. We have two mathematical quantifiers, universal and existential. Note down these equations and dependence and equations in terms of formulas. This is not given in textbooks. Symbols are also not given in textbooks, but we try to remember the symbols and memorize it. Okay students, here we conclude the lecture. The remaining students we will do the next lecture. Thank you students.